Good afternoon, everybody. Good afternoon, everybody. I think nobody has joined today because I did not take the last class, so I think nobody has joined. It's already nearly 3:10, so I won't go for a lot of wait. I'll first give a recap of week 9, what Professor Mohapatra has taught, and then I'll discuss certain questions which will help you in solving your assignment. So, without delaying, I am going to start with a recap of week 9. In week 9, Professor Mahapatra has started taking the classes, and he works in HVNI in the radiochemistry division. So, introduction is as follows, that we know why actinide chemistry. The continued interest in the nuclear power program provides continuous motivation for investigating the chemistry of actinides. Certain fields are nuclear fuel for reactors, recovery from ores, chemical quality control, spent fuel reprocessing, or nuclear waste management, effect of environment, etc. And these are the processes. First, you have the mining of the ore, then you have this form mill, fuel fabrication, nuclear reactor, spent fuel storage, spent fuel reprocessing, waste management, and then this is the whole nuclear fuel cycle. Okay, moving further, what are actinides? Actinides or actinoids, they are called F block elements where the electrons are filled in the 5f orbitals. The actinide series start from AC actinium and it ends with Lr, okay, lawrencium. So if in short they are considered to have similar physical uh, uh, yeah, physical and chemical properties, and uh, though AC does not have any F electron, so it is it is considered part of the series similar to La in the lanthanide series, and general electronic configuration of actinides are 28 18 32. In short, 5s2 5p6 5b10 5f 6s2 6p6 6d and 7s2. Actinides give rise to a decay series such as 4n 4n plus 1 4n plus 2 and 4n plus 3. Okay, moving further, actinides in nature. So it is the Oklo phenomena. Interestingly, Pu is the highest atomic number element to occur in nature. The trace in ppt quantities arise in natural uranium-238 deposits such as one in Oklo. A natural nuclear fission reactor was suggested to have existed in Oklo in Gabon. Africa is discovered by Francis Perrin in 1972. This is the only location where this phenomenon of self-sustaining nuclear fission reaction is known as to be occurred. This is thought to have taken place approximately 1.7 billion years ago and probably continued for a few 100,000 years. So 0.44 60% of the 235 uranium was detected in the U of Oklo mines, and the isotope monitoring was done from burn-up measurement. 99 ruthenium fraction was bored. The reactor operated for several thousand years and stopped thereafter due to lower 235 uranium content and increased neutron poisons. Reasons for criticalities: about 3.1% 235 uranium at that time. So this is the periodic table, and then the discovery of actinized uranium is the earliest known actinized, known as early 79 AD by the Romans, and its oxide extracted. And Discovery of element is credited to the German scientist, and uh, you know uh, thorium was discovered by Morton Smark, and Henri Deverin discovered Ac in 1899. In 1934, 500 milligram of Pa was isolated from pitchblende, but it can be easily formed now by irradiating thorium Pa or thorium Pa and gamma. And Pa is important for the production of uranium 233. Now going to the Neptunium experiment by Edwin Macmillan. There is a question. In 1934, Enrico Fermi published a paper suggesting the discovery of elements 93 after irradiating U with neutrons. This was disproved by von Grosse, who suggested possible production of Pa, and Notfek, who suggested U may be fragmented to 2 or 3 pieces, but Fermi stuck to his claim. Element 93 at that point thought to be similar to the group 7 elements, including manganese and Re. As chemistry did not match that of Re, that claim was proven wrong. Japanese physicists Y. Nishina and K. Kimura bombarded uranium with fast neutrons and discovered 237 uranium with 6.75 days half-life. After fission discovery, Edwin Macmillan wanted to measure fission yields of uranium targets in the cyclotron at Berkeley Radiation Laboratory in 1939. He irradiated uranium target by neutrons from beryllium target bombarded by 8 mega electron volt deuterons. In the 37-inch cyclotron, he observed 2 beta decay half-lives of 23 minutes and 2.3 days. The 23 minutes activity was identified as 2 uranium 239, but what about the 2.3 days activity? So this is a relative activity with the absorption equivalents in per centimeter of the air. And then the discovery of Neptunium by Edwin Macmillan and Abelson, how it carried out. Macmillan carried out the chemistry along with Emilio Serge to prove the chemistry was similar to Re, but with no success. When reacted with HF in oxidizing condition, it behaved like rare earth, including it is a fission product. Macmillan then collaborated with Phil Abelson and reacted with HF under reducing conditions, leading to precipitation like TH, suggesting it is not a rare earth element, and in oxidizing condition it precipitated by NaAC, more like U. Okay. Finally, he concluded. Uh, that the 23 minutes radionuclide is uranium 239, and the 2.3 day what is a new element akin to uranium, and he named it as Neptunium. So, going further for man-made actinides beyond NP, 1940, Seaborg, Wall, Kennedy, and Macmillan discovered element 94 by irradiating uranium with deuterons. The first isotope of Pu to be discovered was Pu 238, 238 uranium plus D giving 238 neptunium plus 2N, beta decay 238 Pu, 238 U plus N giving 239 NP, beta decay 238 Pu. Going further, production of heavier actinides, 12 TPEs were added to the periodic table in the 30 years between 1944 and 1974. Element 95 and 96 were discovered from 239 Pu, 239 Pu 4 helium giving 242 Cm plus N, 239 Pu N gamma 240 Pu N gamma giving Am. So yes, this is how high flux isotope reactor was built at OINL with a flux around 10 to the 15 N centimeters square per second. With transfermium elements, production was difficult. Now these are the certain isotopes of actinide elements: actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, anstinium, fermium, mendelevium, nobelium, lawrencium. So the natural abundance you can see, and what are the main man-made. So then we talk about actinides in the nature in another lecture, week 9. So though thorium, Pa and U are available in nature in large quantities, but Ac and Pu also available in ultra-trace levels. U is in the earth crust around 0.03%, U in the seawater is around 3 parts per billion, thorium is in the earth crust around 0.1%, natural uranium is 0.72% of 235 uranium, depleted uranium is less than 0.72% of 235 uranium, low enriched uranium is 0.72 to 20% of 235 uranium, and highly enriched uranium is 20 to 90%. Okay, and then weapon grade, all this Professor Mohapatra has taught. Then synthesis by neutron capture. This is a whole reaction. Years away radiation needed for production of 1 milligram of 252 californium by irradiating 239 plutonium in 3 into 10 to 14 neutron centimeter square per second. So yes, synthesis of heavier elements by accelerator with good beam current and high energy charged particles are needed. The product is contaminated by fission products. Heavier elements are produced at atom at a time scale. Continuous experiments are needed. Identification is done by parent, daughter, granddaughter correlation. The products are highly radioactive. Solutions are damaged due to radiolysis. High radiotoxicity. Remote handling is must. Identification is difficult. The products have low stability. Few atoms of NO, half-life 1 hour, and LR half-life 3 months are isolated. Now, position in the periodic table is in the late 1930s. Only 4 actinides were known: AC, TH, PA, and U, and the last 3 were placed in the periodic table as another transition series, 6D series, as homologues of HF, TA, and W. Quantum theory of Bohr and other experimental results suggested them to be the part of 5F series. Inconsistency between theory and chemical properties made difficulty in placing them in the periodic table. Alfred Werner in 1905 suggested thorium as the homologue of cerium and sowed the seed for a new series like the lanthanides. After the discovery of NP and PU, and based on their chemical properties, their placement in the 4 transition series was challenged, and it was concluded that they rather were similar to uranium. After the discovery of AM and CM in 1944, similarity between Ln and An was recognized. Similarity in spectroscopic and magnetic properties due to similarity in electronic configuration, similarity in crystallographic properties owing to near matching of the ionic radii. Oxidation states are not similar, and variable oxidation states for early actinides. So in 1913, Rydberg, there was a lot of confusion for the 5F series, by the way, before 1940s. What was the confusion? Transition group should be there around U with 5F element being filled. Then 5F in 1923, Bohr said that 5F series should start with element 94. In 1924, Goldsmith said that up to element 96 should be homologue of platinum group. Segura and Urey in 1926 said that calculation indicated that first 5F electron entry should be for element 95. Wu and Goudsmit did more refined calculation and suggested it could be element 93. Macmillan, Mowley, and Smith said that 5F shell should begin with thorium. Sweeney said that 5 electrons should start with Pa and U. Then Von Graup, Quill, and Goldsmith are there. Moving further, NP and PU behave like U and TH but not like RE and OS. The reason for this is that we know it very well. We know it well. There is no evidence for a volatile plutonium tetroxide in contrast with the volatile osmium and ruthenium tetroxides, and there is no evidence for an oxidation number of 8 in plutonium. The properties of AM and CM were similar to that of the lanthanides and not that of iridium and platinum. The observation of Jack Addison of the isomorphism of the compounds of THO2, UO2, and PO2 and PuO2. MOT is not isomorphic with UO2, and is observation of the regular decrease in radius of the metallic ion in these oxides. The other evidences are magnetic susceptibility of uranium and Pu, sharpness of optical absorption of U and Pu, evidence of organic complexes of U4+ and Pu4+. Analysis of the spectrum of neutral uranium atoms and come to the conclusion that electron configuration of the lowest state of uranium is 5F36D7S2 with the term symbol of 5L6. Now this is similar to the lanthanide series. The electron does not go to the 6D orbital but to the 5F orbital. +4 state was prevalent for thorium, uranium, neptunium, and plutonium, and +3 was also reported. Actinide series differed from lanthanide as higher oxidation state prevailed. Thorium behaved like cerium as both had +4 oxidation state. So Seeberg proposed the actinide concept at like, fortunately I really did not have a reputation to read at that time, and even more fortunate, he was right. So scientific discoveries are always right. So yeah, you can see this is a periodic table. This is lanthanide series and this is actinide series. Okay, moving further, the electronic gas phase configuration. Uh, Radon is considered as a core, and you can see the configuration M3 plus as the ionization energy, 5F6767 from actinium to lawrencium and lanthanum to lutetium in actinides and lanthanides. So information obtained from the parametric susceptibility, parametric resonance, light absorption, NMR, etc. Now these are an electronic configuration energetics. So from the Hartree-Fock calculation, they show the most of the energy of actinide configuration come from the electrostatic interactions between the f electron and the nucleus, which increases with jet actinized contraction. The 7s2 and 6d energies are nearly constant and do not depend on jet. For an less than u, 6d is favorable, but for an greater than u, 5f is favorable on the basis of the binding energy. For the elements in the first half of the F shells, it appears that the less energy is required for the excitation of 5f to 6d than for 4f to 5d. Energies of 5f, 6d, 7s and 7p orbitals are comparable, lead to variable valency. Interaction of fluorine with electrons of uranium was seen by EPR measurement of UF3 in CaF2 matrix. Now in the next lecture, he talked about electronic configuration derived from the spectroscopic studies. So comparison to the lanthanide and actinides elements number 89 to 103, which is AC to LR, is strong resemblance with lanthanides La, Lu. Lanthanides 14 4f electron from cerium, 14 5f electron from Pa, etc., etc. Similarities and differences are as follows: that f orbital as a part of active valence orbitals, Ln and An contraction, lanthanide actinide contraction, GD is 3 dot Cm3 plus F7 configuration, and trivalent state. Now the differences are 5f orbital of actinides are in close energetic proximity to other valence orbital. 6d orbital are energetically accessible. 5f electrons shielded more effectively than 5f electrons, and variable valency in the actinides, which is not a case in lanthanides. Now these are certainly radial distribution plots, and then these are the oxidation states. You can see from cerium to lutetium and from thorium to lawrencium, M3 plus ion configuration is there, which I have added a question to make. Now then there is a redox potential. You can see it is important in deciding the stability of a particular oxidation state. Then the most important is the aqueous actinide chemistry, the water and the radiolysis. How does it happen? It's divalent cation, it's trivalent ion, etc. So please go through them, and I think if you have any confusion, you can write to me. These are the hydration properties, where the primary hydration number, secondary hydration number, and the total water molecules absorbed is in respect to the crystallographic radii, gives Cn coordination number equal to 8, and which is generally formed by XFs or TRLFS. Hydration of the actinyl ions, they are the lower valence state. Spherical ions, higher valence state exist as linear dioxocation. An5 ions can form cation-cation interaction CCI with other ions such as UO2 2+, Dalton transaction PCCP. Now chemistry of uranium to Am, interaction of actinide ions with ligands. Interaction type is mainly electrostatic, ion-ion and ion dipole. Interaction energy measure of the stability constant is proportional to the it is proportional to the charge on the metal line, and the inversely proportional to the distance between the ions. So order of atomic ionic size, actinide contraction similar to the lanthanide contraction, ionic radii decreases with increasing Z, smaller size with increasing Z. One would expect the order of complexation as An6 plus, An5 plus, 4 plus, 3 plus, An6 plus to ANO2 2 plus, An5 plus to ANO2 plus. Finally, the observed order of reactivity is this. The complexation of actinides will be discussed in a subsequent lecture. Before that, the general chemistry should be discussed. Now this is the chemistry of uranium. Uranium exists in the oxidation state of +3 to +6. The last one with the UO2 2 plus ionic species being the most stable. U3 plus a very strong reducing agent in view of soft nature. It forms organometallic compounds such as UCP3, U4 plus obtained by the reduction of UO2 2 plus passing to the yellow uranyl ion solution through zinc amalgam column produces the green U4. So this is how it works. Now this is the chemistry of neptunium. Neptunium is the first trans-uranium element discovered. The important isotopes are these, which hybrids this and this. Plutonium, americium, the americium. You can go through that. These are basic properties, and then in the last lecture, he talked about the oxidation state, and he talked about the effective ionic radii of them, and oxidation state and the coordination number. And after that, he talked about, I guess, the hydrolysis constant, the Kw for both of them, and what should be the water and their dependence on the pH and separation limits. So please go through the classes, and if you have any doubts, please make sure you contact me, and you have to follow this book. This is a book, The Chemistry of the Actinide and Transactinide Elements. So it has the details of every actinide element, and this is a very nice book where you will find detail of everything, the history to how it was discovered, and their properties, etc. So I'll upload it along with, you can go through it if you're interested. So yeah, that's all for the recap. Now let's go with the assignment. As nobody has joined, I will still explain slowly, like I'm recording the video. So yeah, good evening everybody. This is myself is Shresh Gupta. I am your TA, and this is a class like TA-ship based on 10 week 9 classes. There will be 10 to 11 questions, and if you as nobody has joined, there will be no questions at all. So the first question is saying, what is the general electronic configuration of the lanthanides? Okay, so we know lanthanides are above actinides, and what could be the general configuration? So do they have n minus 2f and minus 1d and ns? If they have this, that if what is the number of electrons that they have in the d series? So like, let's go to the answer directly. In the lanthanides, the differentiating electron occupies 4f subshell and rarely found on the Earth's crust, so they are called rares. The general electronic configuration of lanthanides are 6s2, 5d021, 4f1 to 14. So what do you think is the right answer? Figure it out yourself. The right answer will be C, D0 to 1, F is 1 to 14, and 1 is 1 0 to 1. So this is the right answer. Okay. Now going to the next question. Atomic number of actinides are from 57 to 70, 58 to 71, 89 to 103, more than one of the above, none of the above. The correct answer is option number 3, which is 89 to 103. Atomic numbers of actinoids are from 89 to 103. Actinides start from actinium and go till the lawrencium, and that of there are 15 elements. Actinium atomic number is 89. It is often included in group 3, and the F block actinides start from thorium atomic number 90, thus reducing the elements to 14. The term actinide means actinium like, and the elements included are actinium, thorium, PaU, and PPu, Am, Cm, Bk, Cf, Es, Fm, Md, No, and Lr. Okay. And actinides have variable valency, very large atomic and ionic radii, and exhibit an unusually large range of physical properties. All actinides are radioactive in nature, uranium and thorium being the naturally occurring radioactive elements. 58 to 71 atomic numbers belong to the first series of the F block, that of the lanthanide. Lanthanides start from lanthanum, and the last lanthanide is lutetium. But similar to actinium, lanthanum atomic number 57 is not included in the F block and belongs to the group 3. Hence, the F block lanthanides are from atomic number 58 to 71. The lanthanide series includes Ce to Lu. Question number 3. Identify the incorrect match. First one is anilunium, IUPAC official name mendelevium, aniltrium, lawrencium, anilhexium, sevorgium, and anilunium, which is darmstadtium. So which of the following is the incorrect match? Let's see. The answer is option number 2, by the way, D and 4. Let's see how. The concept is, there is the IUPAC nomenclature of the elements which having atomic number above 100. The element name should be in accordance with its atomic number. The name should always end with em. For elements having atomic number greater than 100, atomic number greater than 100 consists of three numerical These numeric roots are put together ending with em. Always a name is assigned in IUPAC to each numerical root, which is called up together according to the position of the numerical root in the atomic number. These names are 1 un, 2 is bi b, 3 is tri t, 4 is quad q, 5 is pent p, 6 is hex h, 7 is sept s, 8 is oct o, 9 is in e, 0 is nil l. For example, code for 8 is oct. IUPAC symbol is given separately to each numerical root. Explanation is unnilunium. Unnilunium is 101, so it has atomic number 101. It has IUPAC official name as Mendelevium. Unnilhexium is unnilhexium 106. It has atomic number 106. IUPAC official name is Seaborgium. Unniltrium, it says IUPAC, its atomic number is 103. Its name is Lawrencium. Ununium is 111. It has atomic number 111 and its official name is IUPAC Roentgenium. Roentgenium. So the incorrect match is ununium, which is Roentgenium, but it is Darmstadtium, which is for an element having atomic number 110. Okay, so that's all. Some questions are: the group oxidation states of lanthanides are what? Whereas for actinides it varies from what to what. Let's see. The right answer is +3. That means the group oxidation state of lanthanides are generally +3. For actinides, it varies from +2 to +7. Neptunium was first produced by which of the following nuclear reaction? A, B, C, or D? Let's see. Neptunium was first produced by the following reaction: uranium-238 plus N. Which of the following reasons are used to get Am4? Ammonium persulfate, H2O2, ammonium metavanate, or sodium nitrite? It is there from the lecture. The right answer is ammonium persulfate. We know very well. Let's go to the next question. The lanthanoid GD exhibits an oxidation state of +3 only because the options are: GD3 plus has a small ionic size and high effective nuclear charge. GD3 plus has 4f0 configuration. GD has a unique electronic configuration. DD has low value of third ionization energy. By the way, the right answer is option number 4. Let's see how. So the concept is the concept of ionization potential. It is an energy required to take out the outermost electron from an isolated gaseous atom. The ionization energy of a chemical element is expressed in kilojoules or electron volts. The energy required to remove the first electron is called first ionization potential. The more stable the atom, the higher is its ionization potential. The ionization potential depends on the size of the atom. The smaller the size of the atom, the higher is the ionization potential. It depends on the size of the atom. Smaller size, higher ionization potential, penetration power. It is easier to remove an electron from the more diffuse shell electron than a less diffuse one. The ease of removal follows the order FDPS. The charge of the species, the greater the positive charge, the higher is the ionization potential. Ionization potential value is directly proportional to the positive charge and inversely proportional to the negative charge. Electronic configuration: it is harder to remove an electron from a stable electronic configuration, full-filled and half-filled. Lanthanized gadolinium belongs to lanthanoids in the periodic table. The lanthanides are F block elements as they have their last electron in 4f subshell. The general electronic configuration is this. They are 14 elements in total. They have stable oxidation state at +3 because 2 electrons are removed from the 6s and 1 electron from the 4f subshell. Explanation is gadolinium has atomic number 64. Electronic configuration is Xe4f7 5d1 6s2. The 4f orbital of gadolinium has 7 unpaired electrons. As the energy difference in 4f and 5d orbital is low, the next electron goes into the 5d orbital instead of getting paired into the 4f. After losing the 2 electrons from the 6s subshell, the 5d orbital remains the only 1 electron. Losing 1 more electron from the 5d orbital will leave gadolinium with a stable half-filled electronic configuration. Thus, the third ionization potential of GD is very low. Hence, the lanthanoid GD exists an oxidation state of +3 only because of low third ionization potential. The next question. The next question is saying zirconium and hafnium, ZR Z equal to 40, HF Z equal to 72 have similar atomic and ionic radii because of what? Why? The reason could be having similar chemical properties, or they belong to the same group, they are diagonally related, or lanthanoid contraction. The right answer is lanthanoid contraction. What is it? The cumulative effect of contraction of the lanthanoid series known as lanthanoid contraction. Lanthanoid contraction causes the radii of the members of the third transition series to be very similar to those of the corresponding members of the second transition series. The almost identical radii of Gerard 160 picometer and HF 159 picometer are a consequence of a lanthanoid contraction. Additional information is the whole periodic table is classified into 4 blocks, namely S block, P block, D block and F block. The elements of F block are also called as inner transition elements. 14 elements following lanthanum are known as lanthanoid series and are arranged in a row at the bottom of the periodic table. While moving from lanthanum and lutetium, the atomic radii decreases. These cumulative effects of contraction of lanthanoid series are known as lanthanoid contraction. This effect causes the radii of the third transition series to be very much similar to those of the corresponding members of the second transition series. Hence, due to this consequence, both these elements occur together, thereby making their separation difficult. Some more questions are there from the assignment. After the synthesis of NP, Emilio Surge proposed his chemistry to be like that of which elements? The answer is Re. It is from the lecture. Go and see it. The extraction of neptunium with 30% TBP at 3 molar HNO3 follow the trend of what? The options are 654, 456, 645, 465. The answer is 645. We know why the 4 is greater than 5. It is already explained in the lecture. Now the last question is, which of these is a disproportionation reaction? The options are 2NP6 giving 2NP5, 2NP5 giving 2NP4, 2NP5 giving NP6 and NP4, none of the above. And the right option is 2NP5 giving NP6 plus NP4. So thank you. That's all for today's class. If you have any doubt, feel free to mail me or WhatsApp me. And as nobody joined today's class, so I will be wrapping up with this only. Have a nice day. Please see the video. Thank you.